Hi, everyone. Welcome to the Tech Talk of Data Warehouses in a Data Lake Architecture. I am Raghu Prabhu. I am a Global Business Development Manager for Data Lakes in AWS. So let's get started. All right. So the agenda for this Tech Talk is we're going to talk about a data warehouse being extended itself into a data lake architecture. So what we're going to do is get an introduction for data lake architecture on AWS. From there, we will get a brief introduction of Redshift, which is AWS data warehouse service. Then we will look into Redshift Spectrum because it's the Redshift Spectrum engine that takes a data warehouse architecture into a data lake architecture. So we're going to learn in depth about this Redshift Spectrum engine. As we learn about these concepts, we're going to take an example and we will walk through that example. After that, we will look at some of the popular use cases where Redshift Spectrum is used, and then we will end. So let's get started. Okay. Given that we are going to talk about data lakes, we need to set a baseline for why are we talking about data lakes? Is it a new concept? What are some of the things that have changed, let's say, in the past 5 years that has made this conversation a lot more relevant today than it was 5 years ago? Cloud has changed everything. We have pretty much limitless storage. We have various compute options, from smaller sized machines to much larger sized machines in GPU type instances. As cloud has given those types of infrastructure, the pricing model is also quite lucrative. It's extremely cost effective, pay as you go pricing models with no contracts. And then the world that we live in today, there is just a lot more data. If you look at the kind of workloads that you had today and the kinds of problems that you're trying to solve today to what it was 5 years ago, then most people will realize that there is just a lot more data today than we did a few years ago. On top of that, we have new breed of analysts and data scientists. Every application design, or any kind of service that anyone is building these days is incorporating machine learning technologies in the application development process. So there is just a lot that has changed in the past 5 years, and the cloud has basically created a platform to make most of these use cases possible. So here we are talking about data lakes. So let's understand what brings us today to this conversation. Like I said, we just have a lot more data today than we did a few years ago. So if you go back again, say 10 years, you will see that most data an organization produced was structured data. By structured data, I mean database type data where there is a schema, there is an application, and the application produced data which went into a database or a data warehouse. Now, if you fast forward to where we are, we have a lot of data, but what kind of data is it? It's because of the devices that we have today. And by devices, I'm talking about obviously the tablets and the cell phones we have. On top of that, IoT devices and all the various applications that go into these devices are creating just a lot of data. And this data is not fully structured data. This data is semi-structured data, like JSON type data, Avro or XML type data. And there is just a lot of data that we can analyze today from these applications or from these devices that tell us a lot about our businesses and our customers. So the data has significantly increased from structured data to a semi-structured data or even unstructured data. And the growth of this data is quite rapid. What we want to do is bring all this data, structured and unstructured and semi-structured data, and be in a position to analyze all of this data. So how would you define a data lake? The definition is actually quite simple. A data lake is a centralized repository that allows you to store all your structured and unstructured data at any scale. With that, what we should do is take a look at a traditional analytics architecture, something that we know quite well from last 20 plus years. So the screen that's there in front of you should look quite familiar. It's a very popular data warehouse architecture where we have a whole bunch of these OLTP type databases moving their data into a centralized data warehouse. And once that happens, you could do your BI and analytics, your dashboarding on top of the data warehouse. Extremely popular architecture, been around for a while, even popular today, but it does have some constraints. Number one, now that we have talked about a little bit of unstructured data, how would you move that in a traditional architecture like this? You cannot, or it's extremely difficult or way too cost prohibitive. So this particular technology has its limits, and it's good for certain things that we already know, but it's not good for something like, that we talked about, such as unstructured data. Which brings us to, let's say, the mid 2000s, once we started getting Hadoop and some of the big data technologies, you will see the analytics stack evolve into something like what you see in front of you. The traditional databases and data warehouses remain, but on top of that, organizations started creating their Hadoop clusters. And Hadoop clusters were pretty much used for unstructured data analysis, and lots of it. But this created its own set of challenges. What it did is it created data silos. And I'm sure a lot of you can relate yourself to data movement or ETL that you would do between all these different data silos, constantly moving data from one system to another for various use cases. That just took a lot of time, a lot of money in just shuttling data around into all these different systems. These are data silos. What we want to do with data lakes on AWS is we want to get rid of these data silos. We want to give you options, the ability to do massive scale analytics. So the way we are going to start off doing all those things is by giving you one single place to put all your data, one single storage system to put all your data. That may be your structured data or even unstructured data or semi-structured data. And that storage service is S3. Amazon S3 is a great cost-effective storage system for all your data. Like I said, all the data structures that I've mentioned. You can bring this data, and as you do, we recommend that you store this data on S3 in open file formats. Open file formats such as CSV, ORC, Avro, Parquet, Grok, JSON, XML. Bring your data from various different sources into one single place, but keep them in open file formats and not proprietary file formats. If you are going to bring your data from various applications and systems and devices into one single place, such as S3, now how does this architecture work in the grand scheme of analytics stack that you already have in your organization? So what we're going to do is just walk through this particular slide. From the left-hand side, you will see something that we just saw previously in our slides, where it's a traditional data warehouse architecture. A data lake architecture on AWS, such as S3, can augment your existing analytics or your existing data warehouse stack. It doesn't have to be a replacement. It can augment your existing analytics stack, which is that's what's quite nice about a data lake architecture on AWS. So they can coexist. So you can continue to bring your data from your traditional databases into the data warehouse, and you can bring some of your, let's say, unstructured data into the data lake storage, such as S3, and start building your data lake. But then there is something interesting that's happening in the industry, which is this horizontal line between the data warehouse and S3. What some of our customers are doing is bring their structured data as well into S3. So S3 becomes this one centralized storage location for all your data in the organization. That may be your structured data or unstructured data. It basically is this one centralized data repo for all your data. So the movement of data from data warehouses or databases into S3 is also a very common and a popular format. Now, if the layer below is your storage layer, as we go up, we have what we call as a data catalog. We will talk about the data catalog in the following slides. We're going to learn about what a data catalog is. But what a data catalog is, it's a metadata store for all your data. So you would keep the schema of your various data locations, such as data in your data warehouse or data in your database or data in your S3, can be cataloged. The schema of all this data can be cataloged in a one single place. And we're going to learn more about that in the following slides. Once your data is cataloged, that's where you start having fun, actually. That's where you will start analyzing your data. So the top layer is all analytics, is the layer where you will pull your data from your data locations, and you are doing analytics, which could be ETL or dashboarding or reporting or machine learning. Those would be some of the use cases that you would bring on top of this data. So the point here is a data lake architecture on AWS can coexist with a data warehouse architecture. If you catalog all this data, then it truly enables massive scale analytics, and we're going to learn a little bit more about it. So, like I said, we need to look at what a data catalog is. A data catalog is a schema repository for all your data in one single place, irrespective of the data location, which may be S3, JDBC sources, which may be your relational sources such as Oracle or SQL Server, MySQL, and even NoSQL data sources such as DynamoDB. So what a data catalog is, it's a schema repository. And this schema repository is a centralized schema repository, and it will point to the places where the data lives, which may be on S3, which may be in relational sources, or it may be even in NoSQL sources such as DynamoDB. In the next slide, I have a screenshot where you will see a typical data catalog. So data stays where it is. Schema is disconnected from the data. So these three separate blocks. Data stays where it is. Schema is separate from the data, and it is put in a centralized data repository. And analytics is the third layer, which you can bring on top of the schema. So each block, each layer is independent of each other. Why would you do that? The reason you would do that is because you would want to create an analytics system that can truly scale independent of each other. So the couple of bullet points that I have here needs to be highlighted. You need to separate your data from your schema so one can evolve independent of each other, which means your data schema can evolve without having to worry about the schema. Your schema, on the other hand, can change independent of the data. So this separation of concerns between data and schema, and if you do that, your analytics, which is the use cases that I mentioned previously, which may be dashboarding, reporting, big data analytics, ETL, machine learning, also called the compute of analytics, can grow independent of the data in scale, and it can grow independent of the schema as well. So a data catalog, a centralized data catalog, which is the schema repository, enables all these different advantages that you will get by creating a data catalog. So, like I said, we're going to look at a typical data catalog in AWS. We have a service in AWS called AWS Glue. AWS Glue is a very popular service among our customers who are building data lakes. And if you look at AWS Glue, it has a lot of components which will help you build the data lakes on AWS. And one of those components is the data catalog itself, which a screenshot of it you're seeing in front of you. The important aspect for me to highlight here is I have a whole bunch of these tables, okay? Number one, these are not real tables. These are metadata tables, okay? And the reason they are metadata tables is because they point to where the data lives. This is the point to where the data lives. And like I said, you can catalog various kinds and types of data. So I got these arrows here. So this particular table is a CSV type data, which lives in an S3 bucket. This particular data is pointing to a table in a Postgres database. This particular data is a table inside a MySQL database. So similarly, I can have some data here that points to, let's say, a DynamoDB table as well. So let's dive deep a little bit in about the data catalog in the following slides. I will take one of those metadata tables and show you the schema and learn a little bit more. But before we do that, let's complete the discussion around data lake architectures on AWS, okay? And what you see in front of you is a typical data lake architecture on AWS. We have already talked about a lot of the concepts of data lakes on AWS, such as structured data, unstructured data, bringing your structured or unstructured data into S3, cataloging this data separate from your data in a service called Glue. And then this particular layer here is your consumption layer or the analytics compute that I keep talking about. So you have seen all these various components already. I'm just bringing all of them together in one single place. So from left to right, you can bring your structured and unstructured data into S3. We haven't talked about glue crawlers, but a quick mention about glue crawlers is if you are to create these metadata tables in the catalog, it would be great if there is an automated way of doing it. And glue crawlers basically do all the heavy lifting in looking at the schema of these different data sources, such as S3 or NoSQL databases like DynamoDB or even relational sources. Crawlers go in, look at the schema, and then create those metadata tables inside Glue Data Catalog. So you don't have to do the create table heavy lifting in the data catalog. That can be done by Glue. So As you're building your data lakes on AWS, your data is on S3 or other locations that I have previously mentioned. Your data is cataloged. Now, you can bring in your ETL workloads. And for that, you could use our analytics service, Glue ETL, to do your ETL jobs. If you want to do interactive query on top of this data, you can use Amazon Athena. For your big data workloads, your Spark, Presto, and Hive workloads, you can connect Amazon EMR to the Glue Data Catalog, because Glue Data Catalog is Hive compatible data catalog. So instead of your Hive metadata stores, you can just bring in the Glue Data Catalog, and it can connect like Hive. You can bring up your big data workloads on top of this data catalog. Then Redshift. We're going to learn a lot about Redshift in this particular webinar. Redshift is our data warehouse, and what we're going to learn is how you can take a data warehouse into a data lake architecture. So we're going to learn a lot about this particular workload. And then last but not the least, machine learning workloads through SageMaker also work with the centralized data catalog in Glue. Finally, I just want to make a quick mention of this. So this particular rectangle that I have on top of the data catalog is something that we are working quite aggressively on, is the centralized governance layer. We call this, we have a service in beta right now called AWS Lake Formation. And AWS Lake Formation will provide you the centralized governance layer where you can do fine-grained access control, where you can vend permissions to tables, column level permissions. All those are built into Lake Formation. So a governance security layer is coming very soon into our data lake architecture. But for the purposes of this particular webinar, we are going to dive deep into this use case where you have a data warehouse, such as Redshift, and you want to query data that is in a data lake, such as S3. So how is that going to work? So a quick introduction for Redshift. Redshift is our data warehouse service. It's a fully managed petabyte scale data warehouse service. It's a MPP architecture, massively parallel processing type architecture, MPP type architecture, columnar data store. So perfect for OLAP type use cases, analytics, data warehouse type use cases. And the way Redshift is structured, again, this is a very simplistic picture of Redshift, but does a great job introducing it to you, is it has a leader node, okay? You interact with the leader node through JDBC and ODBC connectors that we have with Redshift. You interact, you bring your you connect your applications or SQL Workbench query tool, or any query tool that can work with the JDBC or ODBC connector. You use that to connect to a leader node. From the leader node, we have various compute nodes. So as you can imagine, this particular layer of compute nodes can grow. You can have fewer compute nodes if your data warehouse is small. You can keep adding these compute nodes and grow your data warehouse as well on Redshift if you have more data. This compute nodes are broken out into what we call as node slices. Each slice is a combination of compute and storage. Like this particular webinar is not so much about Redshift or Redshift architecture. It is about taking Redshift and then extending your data warehouse use cases into a data lake use case. So I'm going to move on, but feel free to research Redshift and how some of these underlying architectures are. But for the sake of this discussion, it's important to note that when you use Redshift, you are loading data into Redshift. Like I said, these compute slices, compute nodes, have storage built into those compute nodes, and you will load data native to those compute nodes. The reason for that is how you get massively low latency type queries. You can scale, the throughput is pretty high because the data is native to that cluster. So data is loaded into the data warehouse, into the compute nodes in Redshift, okay? So if data is loaded into Redshift and data is native to Redshift, it also means that as your data grows, your Redshift cluster would grow. That statement is true. And that statement is true for pretty much all data warehouses in the world. As your data grows, your data warehouse footprint grows because most data warehouses that give you low latency queries have data native to the cluster. That's what you would want. But this discussion is how can we actually not grow based on the right use case, our data warehouse, but extend our data warehouse into a data lake so your data warehouse, in this case Redshift, can query data that is sitting on S3 because as we had discussed previously, S3 is that centralized data repo for all your data in a data lake on AWS, which means that your Redshift cluster needs to query directly the data that is sitting on S3. So how does that work? Which brings us to the discussion of Redshift Spectrum. Redshift Spectrum is the engine in between the Redshift cluster and S3. And Redshift Spectrum uses the data catalog for the schema. So what I'm doing here is taking everything that we have discussed so far and bringing that into this particular slide. We have learned about the data catalog and the Glue data catalog, which is the AWS's offering of the data catalog, where the schema lives. Spectrum is the engine that is responsible for reading data from S3. And as it reads data from S3, it uses the Glue data catalog, which is where the schema of the data on S3 lives. Okay, so we are going to learn a lot more about Redshift Spectrum. Okay, so like I said, we looked at the Glue data catalog, but we are going to look at the Glue data catalog a little bit more in detail with an example walkthrough. All right, so what we're going to do is in this example walkthrough, let's assume that you have a bucket, okay, called NYC Taxi 101. And under that bucket, you have a prefix called yellow, okay? And what you have done is you have some CSV files in that prefix called yellow. You have created a metadata table called yellow table inside the Glue data catalog, okay? So the first arrow basically tells us that this table, yellow table, is underneath a database, and let me call this thing quote unquote database, okay? It's not a real database because you have to remember this is a metadata store. So think of this database like if you're familiar with Hive, Hive has this concept of a schema. right? So this is like a schema, a way to separate things out. So in Glue, we have a database, and let's call it NYC Taxi. Underneath that database, we have a bunch of tables. For this particular example, we're going to focus on yellow table. And this is where the CSV files of the yellow table are. Because this is a metadata store, data is still exactly where it was, which is on S3. Let's double click on yellow. Let's look at the yellow table and what it looks like. The table is yellow. It's under the database NYC Taxi. The data in this particular bucket, prefix yellow, is a bunch of CSV files. And as we bring the schema of the CSV files, this is what the schema looks like. So as you can see, this looks like a lot like a real database table, with the single difference being that the data doesn't move. Data stays exactly where it is, but this metadata points to the data location. Outside of that, we have column names, we have data types of this particular metadata table. And what we're going to do is bring this metadata, bring this data that is sitting on S3 to be queryable in a Redshift data warehouse without having to move this data, is what we're going to try and do. So how are we going to do that? All right, so we're going to look at some code. Let's assume that you are in Redshift, okay? You have a query tool. Let's take an example like a SQL query workbench. You have that query tool connected to a Redshift endpoint. All right, so you can query Redshift tables now. So that's the current setup. And what you want to do is you want to tell Redshift that you want to bring a Glue data catalog, which is outside of Redshift, completely outside of Redshift. You want to bring a Glue data catalog, and within that Glue data catalog, a database called NYC Taxi into the realm of Redshift. So you can query data that is sitting on S3. So this simple 4 lines will allow you to do that. So let's walk through this. What you're doing here is an external schema, okay? And the yellow table will be that external table. So you are creating an external schema, and let's call the schema ext, okay? From data catalog, which will be Glue, pointing to NYC Taxi database. As you remember, we have a database in Glue data catalog called NYC Taxi, and we will map all of this to a role in Spectrum. But with this particular statement, we should be able to query data that is sitting on S3 using Spectrum. So let's look at some examples. Once I run that statement from the previous slide, the schema ext is created inside Redshift, but this schema ext, as you remember, is pointing to the database NYC Taxi in the Glue data catalog. So I can run a query like this: select star from ext.yellow, where give your predicate clause. Or I can do something, this is quite cool. Select star from ext.yellow, and you can inner join this yellow table, which is a metadata table in Glue with data sitting on S3, but you can inner join that data with a Redshift native table. As I have already mentioned, in Redshift, you load your data natively, so you get the fastest access to low latency queries. But with Redshift Spectrum, which is what we are learning today, you can do a join between a table that is native to Redshift with a table that is external to Redshift. But then how does all these things work together when you run a query? All right. So we got 1, 2, 3, 4 different levels. And I hope at this point, some of these levels are becoming familiar to you. Number 1, let's start here. This is the Redshift layer, the leader node with a whole bunch of compute nodes. The way you would interact with Redshift is through JDBC and ODBC connectors. You would bring query tools or dashboards such as QuickSight or Tableau and connect it to Redshift. So layer 1 is your BI layer. Layer 2 is Redshift. Layer 3 is Spectrum. The nice thing about Spectrum is Spectrum scales itself. If you see this, we have 1, 2, 3, 4, and then an N. Why this is because as you query your data on S3, you don't know how much data you would be querying. You could be querying 10 megs of data, or you could be querying, a terabyte of data. What Spectrum does is Spectrum is smart enough to understand how much data you're querying, and it will scale accordingly. You don't have to worry about it. That's the nice thing about Spectrum. All you would do as a user is connect Redshift to that external database, such as NYC Taxi, create that external schema, and write your queries. So I have a query here, which is select star from one of the previous queries that we have seen. We are going to query a table, an external table, yellow table. So if I'm to issue a statement like this through my BI layer as step 1, this query is sent to the Redshift leader node, which we talked about. That's the place, that's the leader node where all queries are sent to. This leader node, which is this particular block here, determines what tables are being queried, which tables are native to Redshift, which tables are external to Redshift, and it passes on those instructions to the compute nodes. The query plan is sent to the compute nodes. At this point, what the compute nodes do is it does its own analysis. It tries to see how much data each of this compute node is going to query that is sitting on S3. It does this analysis of query analysis of how much data it is going to query that is sitting on S3, and it passes those instructions to the Spectrum layer. Now the Spectrum layer knows that it has to query data sitting on S3, where it is sitting, how much data is actually sitting on S3, instructions like that, and it will scale accordingly based on how much data that you are trying to query. So the Spectrum layer will scan your S3 data, and it will do data pruning. It will select data. It will filter data. It will also aggregate data based on the queries that you're trying to run. It will also aggregate data in the Spectrum layer, and it will push all the data that it has aggregated back into the compute nodes, because maybe you're joining with some of the native tables. So the compute nodes completes the query as issued by you, and the results are sent back to the user. All right. So what we have done is basically walk through the life cycle of a typical Spectrum query, right from the client all the way to Redshift, to Spectrum, to S3, and back. And the most important part here to remember as a user is you're not worrying about the Spectrum layer at all. Spectrum layer manages itself and scales itself. So why would you do any of this? Necessity is the mother of all invention, right? Why would you do any of this? Why did we build all these data lake capabilities on AWS? Why did we build capabilities to extend a data warehouse system like Redshift into a data lake architecture? We do all of this is because our customers have use cases. They are trying to solve problems. So what I've done is this is just the popular type use cases. The list is actually quite long, but these are some of the more popular type use cases where our customers are using Spectrum to solve their problems. So I'm going to go through them one by one. Number one, real-time data analytics. Data is put on S3 from, let's say, a streaming solution, and it is queried through Spectrum. This is extremely popular. I'll give you an example. We have a customer that runs a manufacturing assembly line, and this assembly line has sensors, has data sensors. These IoT type devices continuously stream data into S3. This data on S3, as you can imagine, has a metadata table inside Glue, which is brought into Redshift as an external table. What this allows is continuous querying of data from their BI systems that query this data that is streamed into S3 real time. So this allows the customer to do anomaly detection, real-time anomaly detection, any kind of data analysis that you can imagine, because data on S3 is queryable. So real-time data analytics, extremely popular use case. From there, we will take this to data archival solutions. Like I said, a data warehouse solution can get pretty expensive. Although I must mention that if you compare Redshift to any kind of commercial data warehouse solutions, you will see that Redshift is a fraction of the cost of a commercial data warehouse system. It is cheap, but then you may have solutions where you just don't have the need to load all your data into a data warehouse. So our customers, what they do is they load just the right amount of data into a data warehouse solution like Redshift, and they put the rest of the data on S3, because 90% of the time, you're only querying a fraction of this data. So load the data that you need low latency query throughput native into Redshift, and put everything else on S3. So when you have a need to query that data, you can quickly run a Spectrum query and get access to that data. Which brings us to the third point, cost control. You want to control your costs. If you want to scale your analytics, if you are in the business of scaling your analytics and onboarding more use cases into your analytics stack, and if you are continuously growing your data warehouse footprint as you ingest more data, that is just not the most efficient way of doing things. You need to control your costs so you can actually scale the throughput of your system. Like I said, as you query only a part of your data, load that data into Redshift, put everything else back on S3. The final use case is ETL. We see this is a very interesting use case from our customers where the data is showing up on S3, right? Let's go back to the real-time data analytics. You're bringing IoT data, you're bringing clickstream data from various sources. It ends up on S3. Customers are using Redshift Spectrum for ETL because the skill sets that they have are, let's assume that it is more SQL-based skill sets. They have more data analysts that are comfortable with SQL. So what you would do is you would use Spectrum to query data that is sitting on S3, write a SQL, and you can load that data into Redshift, like a create table as select statement with a whole bunch of transformations in it. Again, an extremely popular use case among our customers to use Spectrum for ETL. These are some of the main use cases that we have noticed, how Spectrum is used, where a data warehouse such as Redshift is extended itself into a data lake type solution. Now, finally, we have come to the end of this webinar, and I want to close bringing the same slide, our data lake slide in front of you, because I would like to show you that a data lake use case, a data lake architecture on AWS is an extremely powerful architecture. And what we have covered, in this discussion is this particular use case, which is the Redshift and Redshift Spectrum use case. If you are to create a data lake on AWS, know that you are future-proofing yourself with all the other use cases. So as your use case, today you may start off with Redshift and Redshift Spectrum, but guaranteed your use cases will change. The throughput requirements of your analytics will only grow. And as those use cases change, we already have the solutions for you that you can just bring on top of your data lake. With that, I thank you for your time and thank you for attending this webinar.